The proof for this theorem is a little bit tricky. And from now on, for convenience, let us denote this sum to be S sub n. So those are all S sub n's. And now we can forget about those non-negative random variables. The thing we have now, S sub n, are non-negative and non-decreasing random variables. And here's the proof. Remember, the goal for our proof is that we want to show the divergence of the expectation implies the divergence of the function. So this is what we want to prove. So the idea would be, so you know this guy goes to infinity. If we could somehow prove that S sub n is greater or equal to some positive constant times this guy, almost surely in some sense, then we'll be able to conclude this. And we only need to show this for large n's. And we have to utilize our condition in some way. Namely, we have to use this somewhere. And observe that the left-hand side is equal to the expectation of Sn minus the expectation of Sn squared. And this somehow gives you a feeling that there's some kind of a subtraction going on in this inequality. And from here you will see the subtraction of Sn by this E of Sn, which corresponds to this first line of our idea. So how is this related to the thing going on in here? So this inequality has to be related to some inequalities in probability theory. And this variance should give us a hint that we probably need to use the Chebyshev inequality. Chebyshev inequality basically tells you that Sn will be somehow close to the expectation of Sn. And that, hopefully, will give you this inequality for some beta. And there must be a reason for this alpha to be greater or equal to 0 and less than 2, which you will see in the application of Chebyshev inequality. So let's give it a shot. You look at the probability of the event where Sn minus its expectation is greater than some multiple of the expectation of Sn. And by the Chebyshev inequality, you have this probability. There will be some coefficients in here which we don't know. In the numerator you get the variance of Sn, and in the denominator you get this expectation squared. So I should emphasize this is a square over the whole expectation. And now you can use this hypothesis. You can conclude that this guy will be less than or equal to C times Borel hypothesis is less than or equal to c times this guy raised to power alpha. Here's the power of 2. And in the end, you will get 1 over e of Sn raised to power 2 minus alpha. You see, here's the place we are going to use the alpha is strictly less than 2. So that this guy, Borel hypothesis, will go to infinity as capital N go to infinity. So that this whole thing will be very small as n is very, very big. And now let's see. We want to get this for some beta greater than 0. So we want for some beta greater than 0, this holds almost surely for large n's. So maybe it'll be enough to put the coefficient 1/2 in here. So you get 4 in here and 4 in here. Actually, this 1/2 will give you some room when you break down this absolute value. So you will see later how we get this eventually. Let's first see where this inequality will lead us to. What we really want in here is that the summation of those probabilities is a finite number, so that we could apply the first part of the Borel Cantelli to conclude the lim sup of these events has probability 0. So we want the lim sup as capital N of this to be of probability 0. Because if this happens, you will see the corresponding lim inf of the complement of this, which says this absolute value is less than or equal to the half of the excitation happens almost surely. If this event happens almost surely, you know that if you break down this absolute value, so this is equivalent to Sn less than or equal to 3/2 of the mean, but greater or equal to half of this mean. And in particular, you get this part true almost surely. And eventually, almost surely, as n goes to infinity. That is a good thing about this idea. But the bad thing is that this probably won't happen. That is because, based on this inequality, you do not know the summation of them. The summation of those probabilities is finite. Because the right-hand side, when you take the summation of the right-hand side, you don't know the infinite sum of this will be finite or not. That is a bad thing. But now, here's a very, very important idea. Instead of dealing with this capital N directly, we are going to pass to a subsequence of integers. If for subsequence, say n sub k, that this sum, the sum of this is finite. Then you know this lim sup with respect to the subsequence n sub case will have the probability 0. And you know how, for that subsequence n sub case, you have this. And that actually is enough for our final goal. That is because, remember, this S sub n is non-negative and monotone non-decreasing. As long as you prove that this guy holds for a subsequence, but the non-monotonicity of S sub n, sorry, this is my mistake, so this should be a limit as n goes to infinity. You will see that this limit is infinity almost surely, as long as you know a subsequence goes to infinity almost surely. So now let's go back to the formal proof. And now let's look at the right hand side. We claim there exists a subsequence n1 less than n2 all the way to infinity, such that the summation of 1 over e of Sn raised to power 2 minus alpha is finite. This is an elementary fact. Do you see why this is true? I would like you to think about it for a while. The reason is that actually something more general is true. So if we have a sequence A sub n going to infinity, converges to 0, then you can always choose a subsequence such that the summation of this subsequence is absolutely convergent. So this is because you can choose n sub k such that the absolute value of a n sub k is bounded, say, by 1 over 2 to the kth power. And when you take the sum of this, you know you have found an upper bound for this infinite sum, which is a finite, because it will be the summation of geometric series. Sorry, I made a typo here, so the subscript should be n sub k. It follows from this claim and this inequality that the summation of this probability, let's denote this event by e sub k. So the summation from k equal to 1 to infinity, where e sub k is equal to this subsequential event, where this Sn minus its mean, taking absolute value, is greater than the half of its mean. So that's the event. And by the Borel Cantelli lemma, part 1, you will see that the probability of this event happens infinitely often, namely the lim sup is 0. So now you get, let me write it down explicitly the lim-Sylvius intersection of unions of E sub case. The case from m to infinity, m is from 1 to infinity. This is 0. And we take the complement. Union m from 1 to infinity, intersection k equals m to infinity of ek complement. This event has property 1. That is because this is the complement of this. Now, what is E sub kc? E sub kc will be the event where S sub nk minus E of S sub nk, taking absolute value, less than or equal to the half of the expectation of S sub nk. And what does this tell you about S sub nk? This tells you that there exists m such that for any k greater or equal to m, this tells you for any omega in here, there exists a m such that for any k greater or equal to m, we have this happens. S nk of omega minus E of S nk absolute value is less than or equal to 1/2 of this expectation, which implies, if you break down this absolute value, this implies this S of nk of omega is greater or equal to 1/2 of its mean, the mean of S of nk. Because this event has property 1, you know this holds almost surely. So here I should be careful that this m actually depends on this choice of omega. However, because m is a positive integer, there are only countable choices for m sub omega, even though omega itself could have uncountably many choices. Because of this countability, because you can always take countable union of sets of measure 0, and you still get the sets of measure 0. So you have the limit of S of nk as k go to infinity is greater or equal to the limit as k go to infinity of this half of expectations, and this part by our hypothesis is equal to infinity. The exceptional sets, the sets where this could possibly fail, is only a set of measure 0. This is true almost surely. So what we have done is that we proved that along a subsequence S sub n converges to infinity almost surely. Because S sub n is non-decreasing, since S sub n is non-decreasing, we have limit of S sub n as n goes to infinity is equal to infinity almost surely. And this finishes our proof. There are mainly two tricky parts. One is the idea of making this choice. We want to find such an inequality where we can bound as if n below by some constant times its expectation for large n's almost surely, so that you can use the hypothesis where this limit of expectations is infinity. And the second beautiful idea is that when we found that it might be impossible to make this sum to be finite, we can choose a subsequence of positive integers such that along that subsequence we have the probability of those events sum up to be a finite number. That's it.